We've seen different types of bipolar junction transistor configurations. We just covered the common emitter. Now we're going to take a look at the common collector. The common collector amplifier, commonly referred to as the emitter follower, is another type of BJT amplifier configuration. The input is applied to the base and the output is at the emitter. There is no collector resistor. The voltage gain of a common collector amplifier is approximately 1, but the current gain is always greater than 1. The figure below shows the common collector circuit with a voltage divider bias. You'll see that's a common theme. Notice that the input is applied to the base and the output is taken from the emitter. So that hasn't changed. We're still dealing with the same type of output configuration. Only difference here, as they said, there's no collector resistor. As far as voltage gain, as in all amplifiers, the voltage gain in a common collector amplifier is defined by A sub V equal V out over V in. For the emitter follower, the V out, the output, is the collector or the emitter current by times the resistor value E. The in is I sub E, the collector, the emitter current times the sum of the internal resistance little r sub E plus the emitter resistor Re. Therefore, the gain is I sub E Re divided by I sub E Re plus Re. The currents cancel and the gain expression then simplifies. So we've seen something like that before with our collector resistors. It's important to notice here that the gain is always less than 1, because the internal resistance R sub E is normally much less than the value of the emitter resistor Re. Then a good approximation for the gain is voltage gain of 1. Since the output voltage is the emitter voltage, it's in phase with the base or the input voltage as a result. And because the voltage gain is close to 1, the output voltage follows the input voltage. Thus, the common collector amplifier known as the emitter follower. Again, let's read that again. The output voltage follows the input voltage, making it known as the emitter follower. Input resistance. The emitter follower is characterized by a high input resistance, which makes it a very useful circuit. Because of the high input resistance, the emitter follower can be used as a buffer to minimize loading effects when one circuit is driving another. So it's good for a cascade of 2 or more stages. The derivation then of the input resistance viewed from the base is similar to that of the common emitter. In this case, however, the emitter resistor is not bypassed. So if you follow this progression here, this derivation, the resistance in is equal to VB by IB. So the voltage across the base and the current, your AC values. So I sub E, Re plus Re over IB. Then we can substitute IE, we can substitute beta AC, IB by the sum, the product of the sum over IB. The IBs cancel out. We're left with beta AC then is the product times the sum. If the emitter resistor is at least 10 times larger than the internal resistance to the transistor, then the input resistance at the base is approximately equal to beta AC Re, because Re can be neglected. In the figure, the bias resistors appear to the input signal to be in parallel with Rin, just as the voltage divider biased CE amplifier that we saw in the previous video, in the previous coverage here for the common emitter. So we have that Rn total is equal to R1 in parallel with R2 in parallel with Rn. And again, remember, rule of thumb, the value is going to be smaller than the smallest. Current gain then, the signal current gain for the emitter follower is I sub E over the source current. Okay, so the emitter current by the source current, where again I sub S is the signal current and can be calculated as V signal divided by R in total. If the bias resistors are large enough to be neglected so that I sub S equals the base current, then the current gain of the amplifier is equal to the current gain of the transistor beta AC. Of course, the same was true for the common emitter amplifier. Beta AC is the maximum achievable current gain in both types of amplifiers. So this is good for both. The current gain is equal to the emitter current divided by the signal current. Since I sub E is equal to V out over the resistance for the emitter resistor, and the source current is Vn over Rn total, I sub A, the gain, current gain, can also be expressed then as Rn total by Re. So we just set the two equal to each other and simplify, solving now using those terms. Power gain then is the product of the voltage gain and the current gain, and we saw that in the last example. For the emitter follower, the power gain is approximately equal to the current gain because the voltage gain is approximately equal to 1. So let's take a look at an example. They want us to determine the input resistance of the emitter follower. Also find the voltage gain, current gain, and power gain. So we did some of these before. So there's our emitter follower circuit, common collector. The approximate input resistance viewed from the base then, Rn, is equal to beta AC times the value of Re, which gives us 175 k ohms. The total input resistance then, again, like we saw before, is the parallel computation of R1, R2, and R3. Again, smaller than the smallest. Well, we have two of them here that are 56 k ohms, so that's just about half of 56 k ohms. The voltage gain then, neglecting the internal resistance of the transistor, is approximately equal to 1. The current gain then, I sub A, is equal to the IE over IS. IE is equal to V out over RE. IS is equal to Vn over Rn total. And the gain for the current, V out Re, Vn Rn total. So since Vn is approximately equal to V out, we have the current gain equal to Rn total by the emitter resistor, which gives us 24.1. Again, no units. The power gain then is equal to the current gain of 24.1. In addition to a common emitter and a common collector amplifier configurations, there is a third configuration called the common base. In the common base configuration, the base is the common grounded terminal. The input signal is applied to the emitter. The output signal is taken off of the collector. The common base exhibits voltage gains greater than 1, similar to the common emitter configuration, but the current gain is always less than 1. The common base configuration is not widely used in amplifier applications. So in the next section, we move from Class A to Class B amplifiers.